Bismillahirrahmanirrahim. The next video is on network layer performance. So we've seen in the lectures how delay will decide the quality of the link. A link that has a very high delay does not have a good quality. And we would like to keep the delay as minimum as possible so that the destination receives the packet faster. So we know that a packet, when it moves from the source to the destination, it will encounter delays, and we have seen that there are 4 types of delays: transmission delay, propagation delay, processing delay, and queuing delay. We are now looking at these concepts in a more detailed perspective. So transmission delay. Now in transmission delay, what it says is that the sender will put the bits in the packet on the line one by one. So let's explain it in this way. So this is our packet at the sender that we want to send to the other side, okay? And this is the link, right? So what the sender is doing, the sender is putting the bits on the line one by one, right? Like this. It's putting the bits. So it put the first bit on the line at time T1, and it may have put the last bit on the line at T2, okay? So that's what it's saying, that so the transmission delay will be T2 minus T1. If you see T2 minus T1, it's actually covering the length of the packet. Okay, so based on that, the transmission delay is given as length of the packet in bits divided by the transmission rate or the bandwidth. Okay, so you will have here packet length, which is the size of the packet in bits, divided by the transmission rate or the bandwidth. Okay, it's also called the bandwidth, bits per second, so it's a bandwidth as well. Okay, so this is about transmission delay. Then we have propagation delay. This is the time it takes the bit to go from point A to point B in the transmission medium. Now this is where propagation delay is different from transmission delay. Okay, in propagation delay, it will change for each transmission medium. And we've seen that, right? So the propagation delay is distance divided by the propagation speed, and the propagation speed that we have here is different for different mediums. Okay, it's, as we mentioned in class, it's different for air, it's different for water, it's different for copper. Okay, it's different for so many different mediums. So you will always have to calculate the propagation delay, even if the wire, this length of the wire remains the same, but the medium changes, or let's say the distance between the sender and the receiver remains the same, but the medium changes. So instead of using wire, you're now using fiber optic, which means it is light, or you're using wireless, which means it's air. In this case, you will have to recalculate the propagation delay because the medium has changed. Okay, so this is what it is. So propagation delay is equal to distance divided by the propagation speed. Then we have the processing delay. And the processing delay means it's the time taken for the middle router or destination host to receive the packet, remove the header, perform error detection correction, and deliver the packet to the output port. Okay, so anytime a packet arrives at either the middle router or the destination, it will have to perform all these tasks. So there is some delay associated with it. So the processing delay, if you see in the figure, just a quick explanation, we have the sender, we have all these routers in the middle, and we have the destination. So the processing delay, you won't have it at the sender, because the sender, the delay will only start when the sender sends the packet out. Okay, so there's no processing delay for the sender. However, there will be for each of these middle routers. So what does it say? It will take out the packet, do the decapsulation, do the error detection correction, and then forward it to the port. So all these middle devices and the destination, they will all have the processing delay, okay? Except the sender, all these will have processing delay. That's what it means. And the processing delay is calculated as the average. So you will be given the value of processing delay. So delay is equal to time required to process the packet at the router or the destination host, okay? So this is about it. Then we have the queuing delay. In this case, you are calculating the delay that has happened because at the router, okay, because the packet has spent time in the input queue and the output queue. So the queuing delay is the time the packet waits at the input and output queue in the router. Okay, so now let's see how do we calculate the total delay. Now the total delay is, first let's see if there are n routers in the route between the source and the destination hosts, okay? So we are talking in here, there are n routers, and in this case, how many do we have? 1, 2, 3, 4, 5. So n is equal to 5, okay, in our case. So the transmission delay, now it says if we have n routers, then we have n plus 1 links, okay? Now we have, as we said, 5 routers. So we have 1, 2, 3, 4, 5, and 6. So we have n plus 1 links, okay? That's what it says. Now because we have all these links here, we have transmission delay will be n plus 1 into the n plus 1 transmission delays for each link, okay, for n routers plus source. Then we also have n plus 1 propagation delays for all the links, okay? So we would have 6 transmission delays in our case, 6 propagation delays, and n plus 1 processing delays for the n routers and destination, okay? So the processing delay will also be n plus 1 for the n routers and the destination. And the queuing delay will be n, because the queuing delay only happens in the routers and not at the destination. So this is why queuing delay will be n into the queuing delay for all routers. So this is about the delay and how we calculate it. Then we have the concept of throughput. Throughput, as we know, is the actual speed of the medium. And we're going to see here how it'll get affected by the different links that exist. So now we're looking at the first case where we have the source and the destination separated by two routers in the middle. So the transmission rate for link 1 is 200 kbps, link 2 is 100 kbps, and link 3 is 150 kbps. So in this case, you initially you get a high speed, then it becomes quite low. The least is 100 in our case, and then it goes up again to 150. So basically you're having is something like this, a high speed and then a low speed and then something a bit higher. So now this link, this is the slowest link, and this link forms the bottleneck, and this is where the speed will suffer. Okay, so in this case, if you want to know the average throughput of this entire line or the entire path, it's going to be the minimum of these three. So in this case, it will be 100 kbps. And why is that? Because even though you have it fast here and here, when the packet comes at this point, it will automatically slow down to this speed. And it will also come out on the other side at this speed. So this is why your throughput will now becomes 100 kbps. Then we have the second case. In this case, you're having throughput 1, you're having throughput 2, and you have these two sides connected using a very high speed backbone network. Okay, it's a very high speed. So the delay in here, you can't ignore it because it's very high speed. It's very high, the speed, as compared to these other two. So the delay is very less as compared to these two ends. So in this case, the average throughput is the minimum of these two again. So whichever is the minimum, you're going to take that one, and that will be the average throughput for this path. Then we have this case where you're having a main link which is 600 kbps that is being shared by three sources sending to three destinations. So you're having three pairs really of source and destination. Okay, three pairs. So the average throughput in this case will be 600 divided by 3, which is 3 for the three pairs of senders and receivers. Okay, and this is because this middle line is being shared by these three connections. Then we have the third one, which is packet loss. Okay, packet loss is the number of packets that have been lost during transmission. The more a packet gets lost, the lower the speed becomes. Why is that? Because the sender has to keep resending the same information again because it was lost. Okay, the sender has to keep sending it again. So in the same time, you're covering less information because you keep repeating the information. So when a router receives a packet while processing another packet, so why do we have packet loss? It's because in this case, we said we have the router, right? We have the router here, and we have the input queue, and we have the output queue. Now in the input queue, you're having all these packets coming in, and we know that they come and they sit here in the buffer, right? However, this size is limited. After a certain point, this will become full. And if this becomes full, any new packet coming in will be dropped. This is packet loss. So the dropped packet will now need to be resent by the sender. And this will cause more traffic in the network and again more traffic, more packet loss. All right, so this was about the network performance. The next video will be IP addressing.